there and tomorrow. Is that okay? Sorry, but the problem is partly that today's Sunday, so security wants to talk about. Monday is not a problem, but Sunday is tricky. We have to leave it. I just be going to the next.
I'll give you a laser pointer as well if you so wish.
Okay.
It's so I actually made 3 posters. I lost them on the way here. So, but I sent them to you electronically, so you can view them anytime you want.
It's gonna
And then send me an email at all.
Somebody sent all the
Any
posters
questions?
electronic. We have all the posters electronic. But you and I are both leaving tomorrow morning.
I didn't understand that.
And everybody send their poster electronically. The whole group.
You suggest that everybody sends it around electronically.
Yeah, because both you and I are leaving early tomorrow.
Yes. Again? If everybody's having with if somebody's not happy with sharing the brochure, that's fine. For those that are happy, I guess you can share them all or send them around on that email. Good, let's move on. Alan.
I'm here.
Welcome, Alan.
Yeah. All right. Well, I'm going to talk about something that there's no controversy about here. So, so maybe it'll go quick here. Okay, so I'm going to give a somewhat personal view of compaction, largely because my group seems to be the only one that kind of works on some of the effects of compaction. Most people would say, oh, it compacts and you lose all your trace elements because the liquid's lost and that's about it. But there's a lot of other interesting things that can occur during compaction. And of course, some of the evidence for compaction are things like bent crystal grains, deformed grains, cases where crystals actually separate into separate grains that are optically continuous, suggesting they were originally another grain, wrapping around other crystals, and so forth. Other evidence includes the fact that in layered intrusions, the rocks tend to be well foliated, but don't show a lineation. And this is just what you'd expect from compaction. Grains will flatten like this, but if they have any kind of long axis, they'll be in random orientations. And that's sort of what you see in layered intrusions. Ones that are more dynamic in environments, you can start to get lineations and such as that. And the other thing is that you do see, as you get this alignment going in the plane of layering here, you start to lose your incompatible elements as well. Okay, but there's also some other bigger things that are compaction related. One is that you don't see cooling joints, okay? That's because the thing is compacting and there's no sense for, there's shrinkage that you would expect just from cooling to cause any cause any fracturing, because it's being compacted as it's cooling, okay? You can also get even larger scale compaction features. That is, in the Eastern Bushveld, you get various domes and trough-like areas. And these have been associated with basically loading and heating of the footwall, which then causes deformation of the footwall that starts to intrude into the Bushveld complex. And as I understand it, they can actually get all the way up into the upper zone here. In an earlier paper, Jim Mangal said bubbles don't migrate in crystal mushes. And I said, hold my gin and tonic. I'm not much of a beer drinker. And so I did an experiment. Let's see if this is going to run here. There we go. There we go. So we're compacting down a pile, and you see that the bubble that originally was stuck down there starts to move as the thing compacts. Okay. So, and it can start to break up and form other bubbles. And so it's important for bubble migration and fluid migration in general. This also happens on a larger scale. This is from a work by my student, Aaron Benson. looking at, and actually this is sort of some of the work by our co-author, Jamie Connolly. Basically what happens when you start to heat up the country rock and fluid migrates upward into say the base of the Bushveld complex. And let's see if I can get this one to run. Is that going to work? Do I have to hit enter? There we go. And so you basically are hitting the country rock below. It starts to heat up. You start to have fluid migrating upward. And what's driving this fluid migration is not just the fact that fluids are buoyant, but it's actually a compaction driven driving the system here. Okay. And if I were a young PhD student and I wanted to do something to make up my mark in the life, I would go and try to use the Bushveld complex as an analog for subduction systems and merge the two. Okay. So anyway, so that's just some of the evidence on all scales that compaction is actually occurring. Compaction models, I'm not going to talk much about those. That could fill up the whole system here. But basically, I can make a couple of points here. Shirley, in 1986, considered a low matrix viscosity and basically defined the systems that we have right here. We have an upper compaction zone where things compact rather quickly, and you can kind of think that is what most people kind of think of as where the compaction is happening. You then have a fluidized zone where liquids are moving up, solids are moving down, but there's actually no differential anisotropic stress on the crystal, so they're not actually being deformed, okay? And that's because basically the crystals can't move down until it loses melt from the system here. And all the melt is being lost from the bottom of the system. And that's what's driving the fluid upwards here. And Mackenzie in 2011 considered a much higher matrix viscosity. And so that this fluidized zone was actually rather trivial. And his system kind of looked like this all the way down. So going from your original liquid fraction to some trivial liquid fraction at depth, but not having this sort of constant system here. So again, most people would say compaction is happening in something like this. This freezes and gives you your trapped liquid component. And this doesn't really happen because it gets frozen in earlier, okay? Oh, and then finally, Connolly and Schmidt in 2022 thought that matrix viscosities are actually somewhat in between the two at about 10 to 17 Pascal seconds. And what he did is, or they did, is made an interesting way of looking at that and looking at basically the half-life of the porosity, which is about 1,000 years or so for olivine and 10 to the 4th, 10 to the 5th years for plagioclase and chromite. Kind of an interesting way of looking at that. Okay. So let's actually look at some evidence for compaction and actually evidence for compaction with crystallization. Because most of these models for compaction, all they do is consider themselves as just looking at grains that are compacting, and they don't consider much in terms of the way of what's happening with solidification here. So this is looking at a Stillwater orthoperoxenite, and this is looking at the composition, and basically it's mostly orthopyroxene, and the little marks here show the composition of orthopyroxene and plagioclase here. Orthopyroxene doesn't change very much, going from a high of about 84.5 down to a low of about 82.5. Well, that's what you'd expect. It's mostly orthopyroxene. That's going to buffer the iron magnesium ratio pretty well here. But if you look at plagioclase, it goes all the way from about 70 down to close to 40% AN component here. And there's actually sort of a couple of bullseyes that it goes here. It takes time for things to crystallize here. Let me just see what my next plot is. And if you look at this, you might say, oh, that's simply a closed system closed system crystallization. Looking at it, you might say that this is texturally a mesocumulate or an orthocumulate here. Cumulate orthopyroxene with a lot of interstitial material. All right. But if you look at estimates of the trapped liquid component, Using the plagioclase abundance, either the norm or the mode, you get something like about 27 to 20% trapped liquid. You looked at the early trapped liquid, the early liquids that are early elements that are not strongly incorporated into pyroxene, such as sodium and aluminum. And here we can even correct for the minus the aluminum that's in the pyroxene. You still get something fairly high, 18 to 21%, 29 to 30% for aluminum here, okay? You look at the late trapped elements, and then you're getting something down with 8 to 10, 14% at the most here. So the idea is if you are compacting and losing liquid as you're going, things that can tell you how much liquid is around, if they get incorporated into interstitial minerals that are crystallizing early, they're going to tell you a much higher trapped liquid abundance, if you will, than are minerals like apatite and zircon that crystallize very late, that suck up all your zirconium and phosphorus, and they're going to give you very low estimates of your trapped liquid proportions. And you can actually model this. Okay, this is a busy figure here. This is looking at temperature and taking a rock that starts out as orthopyroxene plus liquid, letting it crystallize. There's a number of different curves here. This dash one that says AN equilibrium, that's the composition of the AN content of plagioclase if it was actually equilibrium crystallization. It drops down lower than the max because you have some CPX or some calcium being sucked up by the CPX. And of course, plagioclase likes to form zoned minerals. So we can look at another way here. Is this dashed line here, is we can crystallize the interstitial liquid a little bit and then remove the plagioclase. So the plagioclase is undergoing fractional crystallization. The pyroxene is not, okay? And then you get something that follows like this trend. And this trend actually sort of reproduces what we see in terms of the range of plagioclase in the sample. And then you can, but that doesn't explain the phosphorus content, say. So what you can do is the same thing, but every once in a while, remove 10% of that residual liquid that's remaining. And then what you get is something that still follows this red line, still is very similar to the amount of AN compositional sound you see in here. But in this case, you also lose half your phosphorus, okay? So, what this means is, in terms of realistic things, if you were looking at, say, the mg number of orthopyroxene as you go across a mafic, ultramafic transition, such as going from the orthoperoxenite into the lower norite zone of the Stillwater complex, you always see this shift to more iron-rich compositions that's usually been attributed to this iron-rich, re-equilibration with this interstitial liquid, okay? And if you assume that from, say, using phosphorus, that there was a 10% trapped liquid, you would assume that this was at the original iron-magnesium ratio of the pyroxene was, and this was what the original one for the orthopyroxene was. And there's still an offset here, okay? And that's because using phosphorus, you've already lost a lot of your liquid while it was still undergoing crystallization. A more realistic one would be to assume that it was somewhat higher, and you just kind of keep adjusting this until you can get your amount of trapped liquid, effective trapped liquid that the rock re-equilibrated with to give you a smooth trend, okay? Otherwise, what you're going to say is, oh, at the level of the norite zone 1, a new, more fractionated magma came in, but that's not necessarily the case here, okay? Let me know if I'm going over time because I'm going to just ramble here, okay? Just feel free to kick me out. All right, so you can show this in other ways as well. For example, in the Bushveld complex, the characteristic difference between the lower zone and the lower critical zone is a rather trivial increase in the amount of plagioclase. So down here in the lower zone, you don't have much plagioclase. The lower critical zone, you start getting something like you have 3 to 5% plagioclase. And they think that's important, probably because the old people realize that compaction is important and understanding what's going on here, okay? And you can actually model this. And basically what's going on over here, I won't go through all the details, is that down here, the system is compacting before the liquid has a chance to reach plagioclase saturation. And so you don't get much plagioclase forming here. At this point, when you get into the lower critical zone, the liquid is evolved enough that it's closer to plagioclase saturation. Plus it has whatever plagioclase rich liquids that are coming out from below. And so it's going to start crystallizing plagioclase before it has a chance to compact all the way down. Okay. And then of course you get into the point here. And so this can be several hundred meters. And it's not because this liquid that was plagioclase saturated was circulating down. It's simply because of this fact that you're crystallizing and compacting at the same time. Okay. How thick is this mush? This was important for Bundy's talk. This is a model of the thermal profile of the Bushveld complex. We've seen other ones that are something similar to this one here. So the Bushveld complex is this area right here. You get a fairly thick thermal aureole at the base of the complex here. And based on this little red band here is the temperature of crystallization of zircons. Okay, and so they go down to something like almost about 700 degrees centigrade here. So here I am about in the middle of the complex. Of course, I'm liquid here. But these temperatures of zircon crystallization actually go down to the point where we get into the footwall where we actually get partial melting. So the mush zone is not only half all of the crystal pile here, it actually proceeds some distance into the underlying footwall. Okay, other kinds of things that can happen. Well, if you got a system that is cooling from top and bottom, you get other kind of complications going on. This is a model I did with Tony Philpotts, where we basically took a system that was already mostly crystalline, but was starting to undergo compaction, which you could see in the deformation of these plagioclase chain networks that he loved to study. And we were able to show, yeah, well, we can kind of mimic that compaction that we see here. But more importantly, what you see at the top is that because you're freezing it from the top as well as from the bottom upward here, at the top where you freeze it, that limits the porosity and therefore it doesn't want to go down very fast, okay? It's kind of what I call the French coffee press effect. As you press on a French coffee press, it gets harder and harder to compact those crystal grains because they're clogging up the filter. The same thing happens here, but it's because you're freezing this top. And so what happens is you can actually get dilation within your crystal pile, okay? And in this case here, where we find the highest dilation is where you get these segregation sheets. And in the model, we don't have it break open, but in the real world, it's probably separating open and doing something like that. Okay, and you also get the same kind of thing occurring in the crystal tongue of the basement sill in the Dias intrusion here. It came in as a orthopyroxene-rich slurry, cooling from top to bottom. You get the same kind of thing here, compaction in the lowest part, dilation in the upper part, not so much dilation in the very top because that's starting to freeze up. And right where you see the highest dilation is where you get these plagioclase-rich layers as you see right in here. Okay. Okay. Why am I not the wrong button? The other thing that happens, how am I doing for time here? Am I doing okay? Good. Okay, go ahead. Okay. All right.
5 minutes.
Okay. All right. All right. The other thing that can happen as you crystallize, if you're crystallizing in a system that has a change in the bulk density of the stuff that's compacting, such as would occur between going from an ultramafic to a mafic system, basically no plagioclase here to plagioclase bearing here, the density difference between liquid and solid increases by like 50% or decreases by about 50%. And what happens is that as you get to this zone, because the mafic zone doesn't compact as fast, is that liquid can escape from it because the porosity stays open higher, okay? But because the porosity can escape here, that means that you get a zone of low porosity in the very top of your ultramafic section, and that can then act as a trap so the liquid can't get through it and it starts to pond beneath it, okay? And if it's porous, if it's not a perfectly impermeable barrier, it will eventually break down. But this is what you see in a lot of intrusions, especially the smaller ones. This one here is from the Money complex, where you see that the Mg number right at just below the base here is reflecting this high increase in incompatible elements because liquid is getting trapped below that incompatible layer that develops at the top of the zone. All right. And you can also see it in the increase in zircon that we get up here. I think this is important because where do we get PG deposits in these small intrusions? It's not at that contact. It's a few meters below it where we're building up this incompatible rich liquid zone that can act as a trap for any mineralizing fluids that are coming upwards. Okay, there's also microtextural evidence here just to goad my colleagues here. And this is basically kind of that look at that high incompatible elements here. And just she published this back in 2015. And I thought that there was a remarkable similar to what the CPX plagioclase triple junctions were looking like here. She suggested that melt infiltration will cause very small dihedral angles. And that's what you see here. And also that's sort of where your microdolerite here, these small intrusions, you actually get to see frozen in bits of interstitial liquid here. And that's basically right. And the whole thing sort of looks over. In this case here, our system is still undergoing compaction. So the top parts, it's still developing here. Oops, went too far. Okay, so that's it. I'm going to leave you with just one question that I always have. This is what sidewall crystallization looks like. So why doesn't the sidewall compact if it's a kilometer thick pile of crystals? So I just leave that for you to discuss.
Thank you very much, Alan.
I guess I should stay over here so people can hear me. See, I told you there wouldn't be any arguments.
What was your question again? Why is the side wall not?
Why doesn't the side compact? Why doesn't the marginal border group
Cools
compact?
fast and is frozen.
What's that?
It cools faster than the bottom and the top, and it's frozen. It cannot-
Well, that's the conventional interpretation.
Yeah,
Yeah.
I know.
And
No, I'm
also-
just saying that.
And also it sort of collapses, but before it has a chance to act.
Well, I mean, that's the other possibility too. And there's a third one. That perhaps there never really is a big magma chamber, that the thing is slowly opening. Perhaps the third possibility, just to be argumentative here, is that the bush valve or the scare guard is actually opening slowly. And every time it opens it up a little bit, a new magma pulse comes in, mixes with everything that's in there. And that you're just kind of getting something that's slowly opening. And you never really get a big sidewall against a large magma body. Just a suggestion.
Okay, I don't know what to say now. So I will ask if there's some other questions.
Yeah, there's a question.
Yeah, I'm pretty sure that I think it's about your fifth or sixth slide. There was a numerical modeling, numerical model.
This one? Oh. Yeah. Yeah.
Yeah, that's the, so, something that strikes me there is what you seem to be seeing, if I'm understanding that right, is that your percolation is self-organizing in forming fingers.
Yes.
You're not getting a continuous planar layer.
Yeah, that's, I mean, you sort of are. I mean, what you're forming is, again, this is a very simplified system here. The fluid that's being generated is bubbles, okay? The modelists would say that you have a continuous fluid zone, and it's basically starting to, or as you say, self-organize into these channels, okay? And that's true.
And I think, I mean, it makes a lot of sense. I think if you look at sort of models that hydrothermal technologists generate,
Yeah.
star deposits and things like that, they show exactly.
Yes.
It's because the reactive fluid is increasing the permeability, and there's a
Yes.
feedback.
Yes.
Yeah. So I guess the question is, question to John as well. Isn't that what a percolating fluid through a crystal mushroom would look like?
If it were
What
forming,
signature would you expect to find in the box? So could you actually test that?
well, I think there are some observations that suggest that one is you get these in the bushveld, you do get breccia pipes. So these things can become overpressured. And so that would be one example. The other thing, and I think this is why it's important to kind of study these things, is that, of course, we have a lot of isotopic disequilibrium in the lower part of the bushveld. And generally you find that it's the outer rims of the minerals that tend to be have more of a country rock signature than the core of the mineral. So that might be something of evidence for this stuff percolating through. You look at chromites, particularly, that interstitial minerals are invariably show a very strong country signature associated with them. So these are kind of all things that are going on, I think, but I think we need to better understand how does fluid move through these systems. In high temperature metamorphic rocks, somebody can confirm this or not, it takes a long time once the fluid is equilibrated with the rocks chemically for it to actually change isotopically. So I think this is something that's a grand opening for a lot of work to be done. Yeah, was one more question.
You talked in the end about typically mineralizations are found like just beneath the from migrating up. That tends to the crystallization from up down.
Didn't quite understand the question. Did you hear that one?
You talked earlier about the fluid stuff migrating at the upper.
Oh, the mafic ultramafic one here, this one.
Yeah.
Okay, so what's your question?
What prevents fluids from continuing? Is that
Okay, it does. Well, we're just looking at melt here. We're not concerned about fluids right now. Okay, so again, just to explain it yet again here, when you come up to this mafic ultramafic boundary, because there's a density change, there's actually also a bulk viscosity change for the solid. But here we just looked at the density change. Such the mafic rock doesn't compact as fast as the ultramafic rock does. Okay, so that means at the top of the ultramafic zone, the porosity is going to be higher than it is in the ultramafic zone. Okay, and so therefore liquid can get out of there faster because that's more open. You'd get the same thing if the pile stopped growing, the liquid could just escape out the top. Okay, and so what happens is that this liquid can leave the system. Okay, and so it can compact down because it's got an open top, if you will. All right, but now because this has now got lower porosity, the liquid that's coming in below or can't get through it, so it starts to pond there. It would be the same thing if I put a steel plate across here. The solids could still move down, but the liquids would not move up into that, past that plate. And what you would get is liquids ponding beneath that plate. Okay. And so that's what's happened here. Now in this system here, it eventually leaks through. So you get a porosity wave that slowly moves through the system here. And when you can actually see the evidence that it's moving through, if you look at something like the Great Dyke, where it looks like this at the margin of the intrusion, because that's where it freezes fairly fast, but you get into the central part of the intrusion and it's much more subdued because it had a chance for that liquid to escape out before it could solidify.
Happy making.
Yeah.
Good.